Ever wondered how doctors create hyper-accurate 3D models of blood vessels that capture every microscopic detail? It's not just about drawing lines. It's about reconstructing the complex geometry of vascular networks, from the aorta's smooth curves to capillaries' delicate branching. Today, we're diving into a revolutionary approach that's redefining vascular modeling. HUG-VAS, a framework that merges mathematical precision with AI innovation to produce anatomically faithful, editable, and clinically useful 3D structures. Let's start with the problem. Traditional methods for vascular modeling often face two critical limitations. First, they prioritize topological accuracy, ensuring branches connect properly, over surface morphology, the fine details that define a vessel's shape. Imagine a tree diagram. It shows where branches split but misses the bark's texture or leaves curvature. For large vessels like the aorta, where smoothness and precise geometry matter, this can lead to models that are structurally correct but biologically unrealistic. Second, many models rely on latent space representations, mathematical abstractions of shape, that lack the expressiveness to capture vascular variability. It's like trying to paint a masterpiece with only 3 colors. The result is beautiful but not accurate. Enter diffusion models, a cutting-edge AI technique inspired by physics. These models work by iteratively denoising data, starting with a rough sketch and refining it into a detailed image. Unlike older methods, they're flexible and robust, capable of generating highly realistic shapes. But even diffusion models have blind spots. Most focus on topology, the how things connect, rather than surface morphology, the fine-grained details that distinguish one patient's vasculature from another. For example, they might nail the branching pattern of a cerebral artery, but miss the subtle twists or irregularities that could affect blood flow dynamics. So how do we fix this? The answer lies in a fusion of two concepts: NURBS, non-uniform rational B-splines, and hierarchical diffusion modeling. NURBS are mathematical curves used in engineering and design to represent complex surfaces with precision. Think of them as a digital ruler that allows you to sculpt a vase with exacting control over every ripple and contour. By integrating NURBS into the modeling process, we ensure that vascular structures aren't just visually realistic, but also editable, scalable, and compatible with existing medical software. But here's the real breakthrough. The HUG-VAS framework uses a hierarchical architecture to separate the generation of two key components: centerlines, the backbone of the vessel, and radius profiles, the vessel's thickness at each point. This separation is critical because a vessel's width isn't just a function of its path. It's influenced by factors like hemodynamics, surrounding tissues, and patient-specific variations. By modeling these aspects independently, HUG-VAS captures the natural variability between patients, such as how one person's aorta might have a slight twist or a bulge. Let's break down how this works. HUG-VAS begins by generating a centerline, using a diffusion model trained on high-resolution vascular data. This centerline acts as a scaffold, defining the vessel's path through the body. But a vessel isn't just a line, it's a tube. That's where radial profiles come in. These are cross-sectional measurements of the vessel's width at every point along the centerline. HUG-VAS uses a second diffusion model to generate these profiles, leveraging the centerline as a blueprint to ensure consistency. It's like building a road and then determining how wide each lane should be, based on the road's curvature and traffic patterns. Here's where the magic happens. To align the radial profiles properly, HUG-VAS employs an algorithm that acts like a compass at every point along the vessel. This ensures that the cross-sectional measurements remain consistent, even as the vessel twists or turns. It's akin to slicing a spiral-shaped loaf of bread. Each slice maintains the same thickness, no matter how the loaf curves. This alignment is crucial for simulating blood flow, as irregularities in vessel radius can create turbulence or affect pressure gradients. The applications of HUG-VAS are transformative. Imagine a surgeon using a semi-automatic tool to trace a few points on a CT scan, and the system generates a full, accurate 3D model of the aorta. No more tedious manual editing. Or researchers creating synthetic patient cohorts to test new treatments without risking real data. Even more exciting, HUG-VAS can handle zero-shot conditions, meaning it can generate shapes based on vague prompts, like make this artery more curved or add a bulge at the bifurcation. This level of control opens the door to personalized medicine, where models are tailored to individual patients' anatomies. But why does this matter? Consider the implications for bioprinting. Traditional vascular models often fail to replicate the mechanical properties of real vessels, leading to implants that don't function as intended. HUG-VAS's emphasis on surface morphology and variability ensures that bioprinted vessels are not just structurally sound, but also hemodynamically accurate. Similarly, in surgical planning, these models can simulate how a stent will interact with a patient's unique vasculature, reducing the risk of complications. The research behind HUG-VAS is part of a broader trend in medical AI, moving from generic one-size-fits-all models to patient-specific high-fidelity simulations. This shift is powered by advances in diffusion models, NURBS-based geometry, and the availability of high-quality vascular datasets. As these technologies mature, we're not just improving diagnostics, we're redefining what's possible in precision medicine. So the next time you hear about a breakthrough in vascular modeling, remember, it's not just about making pretty 3D images. It's about building tools that save lives, from custom stents to virtual surgical rehearsals. And at the heart of it all is a clever fusion of math, AI, and a deep respect for the complexity of human anatomy. The future of medicine isn't just about treating disease. It's about understanding the intricate dance of biology at a level we've never seen before. And with frameworks like HUG-VAS leading the way, that future is closer than ever.